Hello everyone! Welcome to the mathematical application of neural networks presentation. Today we are classifying vampire numbers with a neural network. On the agenda for today, I will first explain what is machine learning. Next, I will define an ANN, or artificial neural network. Thirdly, we will define what vampire numbers are and break down all the characteristics that define them. Next, we will delve more technically into what a neural network is and how it works. We will then build a neural network TensorFlow for classification, and finally finish off with a conclusion and take any questions. What is machine learning? In the textbook Machine Learning by Zhou, the author describes machine learning as the technique that improves system performance by learning from experience via computational methods. Machine learning is not just a technique, it is a whole field of study dedicated to improving how computers learn. For us humans, there are many examples of how we learn from experience. There's an old adage that goes, experience is the best teacher. Has anyone ever heard that? Well, I think of the many lessons I have learned from experience, like not touching a hot stove because I could get burned. One can liken that to reinforcement learning. Has anyone ever predicted a thunderstorm after a strong stench of sulfur fills the air? I find that I can predict a thunderstorm when I smell sulfur 80% of the time, and a thunderstorm is around 2 hours away. Well, that can be considered a type of supervised learning. Similarly, computers and machines learn the same way, with experience-based predictions, like predicting diabetes based on training from a vast dataset containing labeled inputs and outputs, or recommending movies based on watch history. Now we're going to discuss the different types of machine learning. First up is supervised learning, defined as the technique that uses human-labeled input and output to train AI models. Some use cases for this type of machine learning is training a model to detect vehicle type based on a pre-labeled training dataset. Some examples of supervised learning are classification, neural networks, linear, and logistic regression. Next up is unsupervised learning, defined as the technique utilizing machine learning algorithms to analyze and cluster unlabeled datasets. Some use cases for this are clustering customers based on purchases and common traits. Some examples are k-means clustering, hierarchical clustering, neural networks, and agglomerative clustering. We are doing a neural networks model today, but we are using a supervised learning method. Next up is recommender systems, which is defined as the technique used in machine learning to aggregate like products based on a metric. A metric can be movie reviews. Some use cases are recommending movies a user might like based on previous reviews or watch history. Examples are Netflix movie recommendations, product recommendations based on previous purchases on online apps. And lastly, we are going to talk about reinforcement learning, which is a technique used to map situations to actions in order to maximize a numerical reward signal. Some use cases are a machine playing chess using a system of rewards to make decisions. An example of reinforcement learning would be an autonomous helicopter. Alright, so now we are going to discuss what an artificial neural network, or ANN for short, is. A neural network is defined as a machine learning program or model that makes decisions similar to the human brain, mimicking biological neurons. Just as our biological neural system utilizes synaptic connections to communicate and execute objectives, so too does an artificial network utilize activation functions to pass data through layers to achieve an objective. So let's talk about how that works. Every neural network consists of layers of nodes or artificial neurons. An input layer, one or more hidden layers, and an output layer. Each node connects to others and has its own associated weight and threshold. A node is activated if the output is above a threshold value. If the output is below threshold, no data is passed to the next layer of the network. Today, we will be utilizing the sigmoid activation function for our neural network, defined as y equal to the function of g of z, defined as 1 over 1 plus e to the negative z, where z is the sum of a bias value and the dot product of two matrices of variables and its associated weights. The output is a binary classifier, returning 1 if y is greater or equal to the threshold value, in this case is 0.5, or else it returns 0. When considering whether or not to go surfing, there are several variables to consider. How will the waves be today? Will the beach be crowded? Have there been any recent shark attacks? Let's analyze this simple neural network containing one x variable for each neuron. The decision to go surfing is weighted differently for each variable. For example, the weight of recent shark attacks will be higher than the beach crowd. Additionally, the threshold for activation is different for each variable. The threshold to activate the waves neuron will be smaller than the threshold to activate the shark's neuron. Some use cases of artificial neural networks are image recognition, classification, and voice recognition. Okay, so now we can discuss what vampire numbers are. Vampire numbers are composite natural numbers that possess Fang factors that, when concatenated, is a permutation of the original number. All vampire numbers must have an even number of digits that can be factored into two integers other than 1 and itself. All vampire numbers have at least one pair of factors called fangs, where each XY pair of factors must be half as many digits as the original number. And finally, all vampire numbers have fangs that are a permutation of the original number. The fangs cannot both have trailing zeros. Alright, so now we will do our vampire number analysis, where we look at two numbers to determine if they qualify as a vampire number. First, we look at the number 800. Already, we can see that 800 does not have an even number of digits, so it is automatically disqualified as a vampire number. However, for the purposes of discussion, we will continue down the attributes. 800 is a composite natural number, so those attributes are satisfied. And it does have factors, 20 and 40, the product of which provides the original number. However, 20 and 40 both are not half as many as the original number. Additionally, 20 and 40 are not a permutation of the original number, and they both contain trailing zeros. Therefore, 800 is disqualified as a vampire number. Now we look at the number 1260. It does contain an even number of digits, 4 digits. It is a composite natural number. It does possess factors 21 and 60, both of which are half as many as the original number. 21 and 60 also are a permutation, when concatenated, of 1260. And both factors do not have trailing zeros. For this reason, 21 and 60 qualify as fangs for the vampire number 1260. So now, some of you might be thinking, we're going to classify vampire numbers with a neural network. How does that work? Well, the interval list is going to act as the input layer. And the hidden layer neurons would be discerning between the interval list, whether or not it's a natural number, and then whether or not there's an even number of digits in the number. So these neurons will be activated if these requirements are met, passing on the number to the next hidden layer, right? And so the neuron for the fang will be activated if the number possesses fang attributes. The neuron for the fang permutation will be activated if the fangs are a permutation of the number, and the neuron for fangs having trailing zeros will be activated if one or neither of the fangs have trailing zeros. And then the output layer would be whether or not the number in the interval list is a vampire number. So it will be associated with a 1 and 0 down the interval list. 0 indicating that the number is not a vampire number. 1 if the number has satisfied all the requirements and is a vampire number. And that's how we're going to classify vampire numbers with a neural network. Alright, now for the best part, we can jump into the code. So here are all our imports. We're importing NumPy, Pandas, Math, Random. We're importing TensorFlow and sequential from TensorFlow, dense from TensorFlow, train, test, split from scikit-learn, and logistic regression, as well as scikit-learn metrics such as accuracy score, confusion matrix, classification report. So sequential and dense will be used to build our neural network. Train, test, split will be used to split our test set from our training set. A logistic regression will be used later or at the end of the notebook to compare just how fast logistic regression in comparison to a neural network is. Alright, so now we will move on to populating the interval in a NumPy array. We will be working with the interval of 100,000 to 999,999. Okay. And so we are saving our interval shape into the variable m. The first 4 lambda functions perform vectorized operations on the parameterized array x. For example, the lambda function for summation parses through the parameterized array x and adds up each digit in each index and returns an array with the sum of the associated index. The same goes for count, a 1 in each index if the number in the index has an even number of digits. Okay, and for natural, a 1 in each index of the returned array, indicating whether or not the value of the associated index is a natural number. The last 3 lambda functions return a boolean of the resulting function with the parameterized values x and y. And for half as many, it's x, y, and z, where x and y will be the factors and z will be the value. So we're just trying to see if x and y are half as many as z. Okay. Here we're declaring all the array variables necessary for creating our data set and populating it with zeros. Here we're just verifying that the feature lambda functions are operating. So now we will talk about the getFangs function. The getFangs function takes in a value, the sum of the digits in the value, and the index of the value. So just a quick anecdote. I was first introduced to vampire numbers in my CMSC 412 operating systems class, where we had to find vampire numbers using a multi-threaded program. And in that project, I discovered that in the interval that we're working with, an array of 9, 13, 18, 22, 27, 31, 36, and 40 limits the interval and expedites our ability to find vampire numbers within this given interval, because the values whose sum add up to these numbers are most likely to be vampire numbers. So all vampire numbers in this interval have a sum of digits that add up to one of these numbers, which expedites the iteration time of finding vampire numbers. Now, we're not going to use this interval to limit the interval for the getFangs function, but I'm using this as an introduction into how I'm going to design my neural network. I will be using these numbers to help me classify vampire numbers, okay? But because I want to iterate through each number so that we can get all the features for each value, I'm going to go through the full range of the interval. Okay, so as we go through, we are populating our trailing feature, permutation feature, and half as many feature with zeros. And they will be flagged as 1 once we find a feature for each iteration. We are iterating the range of the past value from 2 to the square root of the value to find factors, okay? So if a factor is found, so let's say we are iterating through the number 100. 2 is a factor. 2 goes into 100 50 times. So if 2 goes into the number and there's no remainders, then it is a factor. So once we find a factor, we will assign the first value to Fang1 and the dividend, or the product of the dividend, into Fang2. Okay? Or the result, I should say, not product. So, and the result of the dividend to Fang2. Now we're calling the trailing, permute, and half as many functions, which returns a Boolean. And we're turning the Boolean into an integer. So if it is a false, it would be 0. If it is true, it will be 1. And we're assigning that to our features variables. Okay. So if all features are flagged as 1, then our value, our past-in value, is a vampire number. And so we will assign the appropriate index of our vampire number array to 1. And just a quick note, because we're dealing with arrays, for some reason I had to plus equals because just assigning it to 1 didn't work. So that's a funny Python behavioral attribute. Okay, moving on. So that's what I did. The trailing feature, if it's 1, it's assigned to the appropriate index. And so goes for half as many feature and permutation feature. Okay, and here we are populating the appropriate Fangs index with the Fangs that were found. And we're printing to console Fang1, Fang2 value, and the trailing feature, half as many feature, permutation feature. So that's the definition for the getFangs function. And now we are calling our lambda functions to populate our arrays for natural number. So each index is flagged as 1 if the appropriate index of the interval is a natural number, which all of them should be because of the interval we're dealing with. But just for future purposes, digit count, we're assigning the array with each index populated with the sum or the digit count of the appropriate interval element. Same goes for the even number of digits, and same goes for digit sum. Here we're doing a list function where we're iterating through each value in the list, in the interval, and we're sending the value, the digit sum, and the appropriate index. Okay, and it will assign the appropriate index with the getThings function result. Let me quickly go back. So here, let me go back here and explain something. So once a vampire number is found, the vampire count is incremented by 1. And we are returning 1 if we have found a vampire number, and returning 0 if we have not. And that's what is happening here. So if we find a vampire number, 1 is assigned to the index, the appropriate index of the parent things array. And if not, a 0 is returned. So we're going to run this now. And here we go. All right. Okay, so we have found all our vampire numbers. And now we're going to print to console how many were found. And we have 148 vampire numbers. Here we are zipping the list of attributes. So we created arrays of the features for each interval element, and now we're going to zip it into one long list to create our data set. All right, so here that's what we're doing. We've created a headers array with the appropriate name for each column, and we're creating a pandas data frame in order to save our data set to CSV. And here we are printing the head of the data frame. Okay, we're going to convert our data frame to integer, and we're printing the head of that. So now we're going to see, we're going to take a look at our rows with the identified vampire numbers. So if the vampire number index is 1, we are assigning the arrays to this variable vamp, and we're printing that here. We're saving to CSV. I'm not going to run the JSON right now. We don't really need it. So we're just looking at what the index 4260 is. I know that it is a vampire number, but just so you see what that looks like, here we have the number. The digit sum is 13. It is a natural number. It has an even number of digits. The half as many feature is flagged as 1. The permutation feature is flagged as 1. The trailing zeros feature is flagged as 1. And our first thing is 260, and our second thing is 401. And it's flagged as a vampire number. So that's what that looks like. All right. Here, we're just reading it from the CSV file that we created, just so I could show you what that looks like, but we don't need to run this right now. All right, so to create our data set for our classification, because all our numbers in our interval are natural numbers, they all have an even number of digits, and the thing 1 and thing 2 is too associated with the vampire number, and so I am dropping these. I created the data set just so that I created the data set with these attributes, so you get a sense of an idea of how to create something like this, but if every number is the same, it's not necessary to create your neural network with it. So that's why I'm dropping these, and I'm assigning it to our X data frame, and I am assigning just the vampire number column to our Y. So the X will be our input dataset and with the label, and the Y is our target label. All right. So we only have 148 vampire numbers, and and the rest of our interval is non-vampire numbers. So we have a very small set of vampire numbers to work with. So our data set at this point is unbalanced, and to balance it, I am going to tile our data set. So the columns, the column with the associated index 1 is going to be tiled. So I'm going to tile it by 6,000 to increase the number of vampire numbers in our data set, so we can classify our data set with a neural network. And now I'm printing our shape. So here is the data set where the vampire number is flagged, and we have 888,000 now after the tiling. And the data set, the number of values where the vampire number is flagged as 0 is 899,851. So now we can see that our data set is more balanced, and it will be easier to split our data set and train our neural network. Now that we have tiled, we're going to recombine our lists. And we are assigning our labeled dataset to X and our target dataset to Y, right? So here we're printing the before and after of the X. We're printing what this looked like. We had our output label 1 here, and we're just taking that off and assigning that to Y. All right. So now that we've recombined our data set with the indexes where our vampire numbers are flagged as 1 and indexes where our vampire number is flagged as 0, we have a shape of 1,787,851. So it's quite a large data set. Okay? Let me make sure I'm running these at the same time. So here I'm dropping. Here I'm balancing our data set. Here I'm separating our features. Here I'm printing a shape. Okay. Alright, so now that our data set is clean, balanced, now we can start splitting our data into training and test sets. We are importing our train test split function from the scikit-learn model selection, and we're using it to split our X dataset and Y dataset into testing and training. Okay, here let's run that. Our random state is 42, so we can recreate this. And our test size is 20% of our original data set. So, here we go. And we've ran that. So at this point, the original number is part of our data set, but I'm not going to use the original number to train the neural network. All I want to use is the digit sum, the trailing zeros feature, permutation feature, and half as many feature. Okay, so that here I am taking the original number out and putting it in another data set so at this point the original number is part of our data set, but I'm not going to use the original number to train the neural network. All I want to use is the digit sum, the trailing zeros feature, permutation feature, and half as many feature. Okay, so that here I am taking the original number out and putting it in another data set so that I can backtrack with the appropriate index once I've trained my neural network what the original number is. Okay, so to train my neural network though, I'm going to take these numbers out, and that's what I'm doing here. Alright, and now we are creating our model using our sequential object from Keras. And our input shape is 4 attributes, and we're using the dense with the sigmoid activation function. And now we're creating our model summary. And here we are seeing the original weights that was populated with our model once we created it. So here are the random weights that were given, and once we run our model, it will automatically perform a gradient descent and find the appropriate weights and bias values in order for us to classify our vampire numbers correctly. Alright. So we are normalizing our data set in order to improve performance and data integrity, and that's what we're doing here. And now we are compiling our model and training that. And so let me go deeper into what is happening here. We're using the binary cross entropy for our loss function, and we're using the atom optimizer with a learning rate of 0.01. And we're fitting our model with our normalized X dataset and our Y training, the output label with the Y training dataset. Okay, and we are using 10 epochs in order to minimize our losses. And as we are going down, we can, as the model is compiling, we see that the loss function is reducing. So I'm fast forwarding a bit here, but as we can see, we're at 5 minutes into training our neural network. So this is quite a long process. Right, so it took about 12 minutes to run our neural network. It does take a bit of time, and so neural networks are best for classifying images, audio, text. I'm using neural networks in this scenario just to have an easy foundation to explain how they work. The best method for this classification is logistic regression, and we will go further into why that is a little bit later. But for now, let us look at our results. So now that our model has been created, here we can recheck our weights to see what they are, and we can see they've changed in order to minimize our loss. Here we are normalizing our test data set so that we can get our predictions. And here we will run our predictions. And we're passing in our normalized test data set. Okay. Okay. Now that we have our predictions, here we're going to get the vampire numbers associated with our test set, just the number, and we're going to map our predictions, and now we're going to print the number and the prediction and the actual. So, right, so 829,696 is predicted to be a vampire number, and it actually is a vampire number. 601,309 is not predicted to be a vampire number, and it's not a vampire number. So here we're looking at our metrics. We're looking at the accuracy score and our confusion matrix and our classification report. Okay. So here we our precision we have as 100% recall. No recalls. Our F1 score is 100%. Our accuracy is 100%. We were able to classify correctly all our vampire numbers. And so here I just want to quickly show how fast running logistic regression is. And so keep it right. That was just a couple of seconds, under 3 seconds, 2 seconds, yeah, so logistic regression is the best tool for this project, but I did think that classifying vampire numbers would be very cool with the neural network. So one more thing I wanted to add, there are times when having 100% accuracy score is indicative of data leakage, and that's something that I'm going to be talking about in our next event, so please stay tuned for that. But for now, we're just going to be really happy that our accuracy score is 100%, and we're going to get back to our presentation. So for our conclusion, we have defined what machine learning is and what artificial neural networks are, or ANN for short. We have defined vampire numbers and all of their attributes, and we have classified vampire numbers with TensorFlow and created our neural network. Alright, so unfortunately, I had to redo this video because I didn't appropriately record during the live event, and so I had to record everything over, and I lost my Q&A footage. So if there are any questions about accuracy, about tiling, or about data manipulation, please don't hesitate to email me at arewa@neuraltransformers.org. So thank you for staying tuned to our machine learning applications in mathematics, neural network vampire numbers classification. This was presented to you by Miami Machine Learning. Don't hesitate to email me at arewa@neuraltransformers.org if you have any questions. Thank you and have a great day.